high above the quiet curve of the earth, beyond the drifting clouds and the soft blue glow of the atmosphere, space unfolds in silence. There is no wind there, no rustling leaves, no distant hum of cities. Only a vast, steady stillness stretches outward in every direction. Stars rest in the darkness like scattered grains of light, steady and ancient. Against this deep black canvas, a gentle warmth radiates from a single star where sun, casting its patient glow across a family of worlds that move in slow, graceful paths around it. From afar, the solar system appears calm and orderly. Planets circle in wide arcs, each following an invisible track shaped by gravity. There are no sudden movements, no hurried motions. Everything proceeds with quiet consistency, as it has for billions of years. The story of the solar system begins long before Earth had oceans, long before mountains rose or life stirred in shallow seas. It begins in a cloud. About 4.6 billion years ago, a vast cloud of gas and dust drifted through a spiral arm of the Milky Way galaxy. This cloud, called a nebula, was mostly made of hydrogen and helium, the simplest and most abundant elements in the universe. It also contained traces of heavier elements, carbon, oxygen, iron, formed long ago in the hearts of older stars. For a long time, the nebula remained diffuse and quiet. But eventually, something disturbed its balance. Perhaps a nearby star exploded in a supernova, sending a ripple through space. The shockwave may have gently compressed part of the cloud. Under the influence of gravity, the compressed region began to contract. As it contracted, it spun. This slow rotation caused the cloud to flatten into a disk, like a vast, misty whirlpool. At its center, material gathered more densely. Gravity pulled gas and dust inward, increasing the pressure and temperature. Over time, the central mass grew hotter and brighter. When the temperature in the core became high enough millions of degrees, hydrogen atoms began to fuse together. In this process, called nuclear fusion, hydrogen nuclei combine to form helium, releasing tremendous energy. A star was born. The sun began to shine. Around the newborn sun, the remaining gas and dust continued to circle in a flattened disk. Within this spinning disk, tiny particles collided and stuck together. Dust grains became pebbles. Pebbles gathered into larger clumps called planetesimals. Over millions of years, these bodies merged and collided, slowly building the foundations of planets. Closer to the sun, where heat was intense, only rocky materials could remain solid. Metals and silicate minerals formed the building blocks of the inner planets. Farther away, where temperatures were cooler, ices could also exist. Frozen water, methane, ammonia. In these colder regions, larger and more massive planets took shape. This gentle sorting of materials created two distinct neighborhoods: the inner rocky planets and the outer gas and ice giants. Nearest to the sun is Mercury, a small, dense world marked by craters and long cliffs. It circles the sun quickly, completing an orbit in just 88 Earth days. With almost no atmosphere to hold in heat, Mercury experiences extreme temperatures, scorching during its long days and freezing during its equally long nights. It is a quiet, airless world, shaped by ancient impacts and the steady pull of the sun. Next comes Venus, similar in size to Earth, but wrapped in a thick blanket of carbon dioxide clouds. Beneath these swirling clouds lies a surface of volcanic plains and rugged highlands. The dense atmosphere traps heat in a powerful greenhouse effect, making Venus the hottest planet in the solar system. Though its surface is harsh, its slow rotation and heavy clouds give it a mysterious, muted presence as it drifts around the sun. Third from the sun is Earth, a planet of liquid water and shifting continents. Its atmosphere, balanced and protective, allows temperatures suitable for oceans and life. From space, Earth appears blue and white, with swirling weather systems and glints of sunlight reflecting off seas. It is the only known world where life has taken root, transforming the atmosphere and shaping the land over immense stretches of time. Beyond Earth lies Mars, often called the Red Planet because of iron-rich dust covering its surface. Vast deserts stretch across its terrain, interrupted by towering volcanoes and deep canyons. Evidence suggests that long ago, liquid water once flowed there. Rivers carved channels, and lakes may have filled basins. Today, Mars is cold and dry, its thin atmosphere unable to hold much warmth. Yet, it remains a place of quiet interest, preserving hints of a wetter past. Between Mars and the next planet lies the asteroid belt, a broad region filled with rocky remnants left over from the early solar system. These asteroids vary in size from small boulders to dwarf planets hundreds of kilometers wide. They orbit the sun in the same general direction as the planets, each following its own steady path. The asteroid belt is not crowded as often imagined. Vast distances separate most objects. It is more like a sparse field of drifting stones than a dense swarm. Beyond the asteroid belt, the solar system grows larger and colder. Jupiter dominates this outer region. It is the largest planet, a gas giant made mostly of hydrogen and helium. Its immense gravity shaped much of the solar system's early development. Jupiter's strong pull may have influenced the formation of the asteroid belt and helped shield the inner planets from frequent impacts by redirecting comets and debris. Its atmosphere is banded with swirling clouds, moving in broad stripes of white, orange, and brown. Within these clouds, storms churn. The most famous of these is the Great Red Spot, a vast storm system that has persisted for centuries. Jupiter has no solid surface in the way rocky planets do. Instead, its gaseous layers gradually thicken with depth, eventually becoming a dense, hot interior. Orbiting Jupiter are dozens of moons, some icy, some volcanic, some potentially harboring subsurface oceans. These moons form a complex system of their own, miniature worlds circling a giant. Saturn follows, slightly smaller than Jupiter, but known for its elegant ring system. The rings are made of countless particles of ice and rock, ranging from tiny grains to house-sized chunks. They orbit Saturn in a thin, flat plane, reflecting sunlight with a pale glow. Like Jupiter, Saturn is a gas giant, composed mainly of hydrogen and helium. Its low density means it would float in a vast ocean, if such an ocean could exist. Beyond Saturn are Uranus and Neptune, often called ice giants. They are composed of heavier elements and ices, mixed with hydrogen and helium. Uranus rotates on its side, its axis tilted dramatically, causing extreme seasonal changes as it orbits the sun. Neptune, deep blue in color, is known for strong winds that race through its atmosphere at remarkable speeds. Past Neptune stretches a distant region known as the Kuiper Belt. This area contains icy bodies and dwarf planets, including Pluto. These objects are remnants of the solar system's formation, preserved in the cold outer reaches. Farther still lies the Oort cloud, a vast spherical shell of icy bodies, thought to surround the solar system at enormous distances. From this distant reservoir, long-period comets sometimes begin slow journeys toward the sun. All of these worlds, from the smallest asteroid to the largest planet, are bound together by gravity. Gravity is the quiet force that shapes the solar system's structure. It keeps planets in orbit and holds moons close to their parent worlds. It governs the rhythm of celestial motion, steady and predictable. An orbit is not a perfect circle, but an ellipse, a slightly stretched shape. Each planet moves faster when closer to the sun and slower when farther away. These patterns were first carefully described by early astronomers who watched the skies night after night, recording the subtle shifts of wandering stars. So, heard a taxter more plövaft to swelt day stortiteveration. It like hadion, because you store many get the paith, our not sprating. How were you cane on the cough coat so beetle like, noun the paste, and all think the monad. It continues to evolve, though changes occur on timescales far longer than a human lifetime. Moons drift gradually outward. Asteroids collide. Comets shed material as they approach the sun, forming glowing tails of gas and dust. Even the sun itself changes slowly. It converts hydrogen into helium in its core, releasing energy that radiates outward as light and heat. This process has continued steadily for billions of years and will persist for billions more. Eventually, long in the future, the sun will exhaust much of its hydrogen fuel and expand into a red giant. But for now, it remains stable, a middle-aged star in a vast galaxy. The solar system occupies a small corner of the Milky Way, orbiting the galactic center once every 230 million years or so. As it travels through the galaxy, it carries its family of planets along, each one maintaining its quiet path around the sun. In the stillness of space, motion is constant, yet unhurried. Planets turn on their axes, creating days and nights. They circle the sun in predictable cycles. Moons trace delicate loops around their parent planets. The entire system moves together, bound by gravity and shaped by ancient events. Seen from afar, the solar system resembles a great cosmic clock. Each component has its rhythm. Mercury circles swiftly. Neptune takes 165 Earth years to complete a single orbit. Jupiter's massive presence influences countless smaller bodies. Even tiny grains of dust respond to sunlight and gravity, drifting in subtle patterns. This balance between motion and stillness gives the solar system its calm character. There are storms and collisions, eruptions and impacts, but on the grand scale, everything follows gentle laws of physics that do not hurry or hesitate. In this vast arrangement, Earth is just one small world among many. Yet, it is connected to all the others through shared origins. The iron in Earth's core was forged in ancient stars. The water in its oceans may have been delivered by icy bodies from distant regions. The same gravitational forces that guide Jupiter also keep Earth in its orbit. As the sun's light spreads outward, it fades gradually with distance. The inner planets receive strong warmth. The outer giants drift in cooler twilight. Beyond them, sunlight becomes faint, and the stars shine more clearly against the dark. The Starbee's hearts, though immense by human standards, is only a tiny fraction of the universe. Beyond its boundaries lie other stars, many with their own planets. Yet, this particular system is home, a structure formed from a single cloud, shaped by gravity and sustained by the steady fusion at its center. In the quiet of space, there is no sound to mark the passage of time. Only motion continues, smooth and continuous. The planets remain in their paths. The sun continues to shine. And the vastness beyond, knowing's in patient silence, holding the solar system in its gentle, enduring embrace. The steady motion of the planets continues without interruption, each world following the same ancient paths traced billions of years ago. The sun remains at the center, its light spreading outward in widening circles, touching rock, cloud, ice, and dust. From this quiet center, the deeper patterns of the solar system begin to reveal themselves. Patterns shaped not only by gravity, but by subtle interactions, hidden interiors, and quiet exchange of energy. At the heart of everything lies gravity, a force that is both simple and profound. Gravity arises from mass. Any object with mass attracts other objects with mass. In everyday life, gravity is felt as the steady pull toward the ground. In space, gravity governs the architecture of entire systems. The sun contains more than 99% of all the mass in the solar system. Because of this, its gravitational influence dominates. Planets fall continuously toward the sun, yet they also move sideways at great speed. These two motions combine to create orbit. Instead of plunging inward, each planet curves around the sun in a stable path. It is a delicate balance between falling and moving forward. This balance can be imagined as a quiet dance. If a planet were to slow down, it would spiral closer to the sun. If it moved too quickly, it might drift farther away. But the laws of motion, described centuries ago by careful observers and mathematicians, ensure that the paths remain steady. These laws are not enforced by intention. They are natural consequences of mass, distance, and motion. Each planet also rotates on its axis. This rotation creates day and night. On Earth, one rotation takes about 24 hours. On Jupiter, a day lasts only about 10 hours, despite its enormous size. On Venus, rotation is extremely slow, taking longer than its journey around the sun. These differences arose from early collisions and the distribution of angular momentum, the conserved quantity that describes rotational motion. Angular momentum is a quiet but persistent property. When the original nebula collapsed and began to spin, that spin had to be conserved. As material gathered into smaller bodies, each one carried part of that original motion. This is why most planets orbit in the same direction and rotate in roughly the same way. They remember the spin of the cloud from which they formed. Deep inside the planets, conditions vary greatly. The inner rocky planets, player bait fuctus Mercury, Venus, Earth, and Mars, share a layered structure. At their centers lie metallic cores, mostly iron and nickel. Surrounding the core is a mantle of solid but slowly flowing rock. Above that lies a crust, thin compared to the planet's overall size. On Earth, heat from the interior drives slow convection currents in the mantle. Hot material rises, cools, and sinks again in a continuous cycle. This motion moves tectonic plates at the surface. Over millions of years, continents shift, mountains rise, and ocean basins open and close. The surface appears stable over short timescales, but it is always in motion. Mars, smaller than Earth, cooled more quickly. Its internal activity diminished over time. Today, it lacks active plate tectonics. Its largest volcano, Olympus Mons, remains as a silent reminder of a more geologically active past. The reduced gravity of Mars allowed this volcano to grow much taller than any on Earth, rising gently over a broad base. Venus presents another variation. Though similar in size to Earth, its surface conditions are drastically different. Its thick atmosphere traps heat so efficiently that surface temperatures remain high enough to melt lead. The lack of liquid water means there is no ocean to help regulate climate or erode rock. Volcanic features cover much of its surface, suggesting episodes of intense geological renewal. Mercury, closest to the Sun, has a disproportionately large core relative to its size. Some scientists think that early collisions may have stripped away much of its outer layers, leaving a dense metallic interior. Its surface bears the scars of countless impacts, preserved in the absence of weather or tectonic reshaping. Moving outward again, the gas giants reveal a different internal structure. Jupiter and Saturn do not have solid surfaces in the conventional sense. Instead, their atmospheres gradually transition into deeper layers under immense pressure. Hydrogen gas becomes compressed into a liquid state. In Jupiter's deeper interior, hydrogen may even become metallic, conducting electricity like a metal. This metallic hydrogen contributes to Jupiter's powerful magnetic field. Magnetic fields arise from the motion of electrically conductive fluids inside planets. On Earth, the liquid outer core generates a magnetic field that extends into space, forming a protective bubble called the magnetosphere. This field deflects charged particles from the sun, shielding the atmosphere from erosion. Jupiter's magnetic field is far stronger, stretching millions of kilometers into space. It traps charged particles, creating intense radiation belts around the planet. Saturn, Uranus, and Neptune also possess magnetic fields, though their orientations and strengths vary. The ice giants, Uranus and Neptune, contain large amounts of water, ammonia, and methane, ices deep within their interiors. These substances, under extreme pressure and temperature, behave in unusual ways. Methane in their upper atmospheres absorbs red light, giving both planets their blue appearance. Uranus rotates on its side, tilted about 98 degrees. This unusual tilt likely resulted from a massive collision early in its history. Because of this orientation, its poles experience long periods of sunlight and darkness as it travels around the sun. Seasons on Uranus are extreme and prolonged, lasting decades. Neptune, farther still, receives only a small fraction of the sunlight that warms Earth. Yet it radiates more energy than it receives, suggesting internal heat sources. Its atmosphere hosts powerful winds and dynamic storms, even in the dim outer reaches of the solar system. Between and beyond these planets, smaller bodies contribute to the solar system's quiet complexity. Moons, for example, are abundant and diverse. Earth has one large moon, formed likely from debris after a massive collision between early Earth and a Mars-sized body. The moon's gravitational pull influences ocean tides, creating a steady rise and fall of water along coastlines. Jupiter's moons include volcanic Io, icy Europa, and massive Ganymede. Saturn's moon Titan possesses a thick atmosphere and lakes of liquid methane. These moons are not merely companions. They are worlds in their own right, shaped by gravity, chemistry, and time. Tidal forces play a subtle but powerful role. When a moon orbits close to a planet, gravity pulls more strongly on the near side than the far side. This difference stretches the moon slightly, generating internal friction and heat. On Io, tidal heating drives constant volcanic eruptions. On Europa, it may keep an ocean liquid beneath an icy crust. Comets for another quiet reminder of the solar system's formation. These icy bodies originate in distant reservoirs like the Kuiper Belt and the Oort cloud. When gravitational interactions send them inward, they approach the sun on elongated orbits. As they warm, ices vaporize, releasing gas and dust that form glowing comas and tails. The tails always point away from the sun, shaped by solar wind and radiation pressure. Asteroids, though smaller and often irregular in shape, carry clues about the early solar system. Some are remnants of bodies that never formed into planets. Others are fragments from past collisions. Occasionally, gravitational nudges alter their paths, sending them into the inner solar system. Over Earth's history, impacts have influenced climate and life, though such events are rare on human timescales. Time in the solar system flows differently than in daily human experience. Processes unfold over millions or billions of years. Mountains rise and erode. Atmospheres form and dissipate. Orbits shift slightly under gravitational interactions. The moon slowly moves farther from Earth, increasing its distance by a few centimeters each year. Even sunlight itself has a rhythm. The sun undergoes cycles of magnetic activity approximately every 11 years. During peak activity, sunspots become more numerous and solar flares may occur. These bursts release energy and charged particles into space. On Earth, they can produce auroras, soft curtains of light shimmering near polar regions. At a deeper level, the sun maintains equilibrium through a balance between gravity and pressure. Gravity pulls inward, compressing the star. Nuclear fusion in the core produces energy that pushes outward. As long as these forces balance, the sun remains stable. This equilibrium has endured for billions of years, providing consistent light and warmth. The solar system is also shaped by resonance, gravitational relationships between orbiting bodies. When orbital periods form simple ratios, their gravitational pulls can reinforce each other. This can stabilize orbits. For example, some gaps in the asteroid belt correspond to resonances with Jupiter's orbit, where repeated gravitational tugs have cleared material away. These subtle patterns create structure within apparent simplicity. The solar system is not chaotic, though it contains many moving parts. It is governed by physical laws that apply equally to dust grains and giant planets. Beyond the visible planets, the heliosphere marks the boundary where the sun's solar wind meets the interstellar medium. The solar wind is a stream of charged particles flowing outward from the sun in all directions. It creates a bubble around the solar system, shielding it partially from cosmic radiation. This bubble extends far beyond Pluto, forming a protective envelope that travels with the sun as it moves through the galaxy. Space between planets is not entirely empty. It contains sparse particles, magnetic fields, and sunlight. Yet, compared to Earth's atmosphere, it is an almost perfect vacuum. In this near emptiness, motion continues silently. Each component of the solar system, from the fiery core of the sun to the frozen edges of the Oort cloud, participates in a grand but gentle system. There is no conductor directing it, no external guide. Only gravity, motion, energy, and time. As the planets continue their orbits, they trace patterns that repeat with quiet regularity. Eclipses occur when bodies align. Tides rise and fall. Seasons shift as axial tilts expose different hemispheres to sunlight. These cycles are predictable, steady, and deeply woven into the structure of the system. The solar system, viewed from a distance, may seem unchanging. Yet within its stillness lies continuous transformation. Atoms fuse in the sun. Magnetic fields shift. Moons experience internal heating. Dust drifts between planets. All of this unfolds without sound, without urgency. The vast distances soften every motion. Light itself takes time to travel, from the sun to Earth, about 8 minutes. From the sun to Neptune, several hours. Across the solar system, time and space stretch gently, allowing events to unfold at a pace far removed from daily concerns. In this quiet cosmic neighborhood, balance persists. The sun shines steadily. The planets revolve. Moons circle faithfully. The outer boundaries remain cold and distant. The motion continues, as it always has. The planets remain suspended in their quiet paths, turning gently in the steady light of the sun. Nothing in the solar system stands apart from the rest. Each world, each moon, each drifting fragment of ice or stone participates in a shared balance that has endured for billions of years. The sun, though constant on human timescales, is slowly changing. Deep within its core, hydrogen nuclei continue to fuse into helium. With each fusion reaction, a small portion of mass becomes energy. This steady transformation has powered the sun since its birth. Over immense spans of time, the proportion of helium in the core gradually increases. Helium accumulates as an ash of fusion. As hydrogen becomes less abundant in the central region, the balance between gravity pulling inward and fusion pushing outward slowly shifts. The sun responds gently. Its core contracts slightly, increasing temperature and pressure, which allows fusion to continue in surrounding layers. For now, this adjustment is subtle. The sun brightens very slowly over hundreds of millions of years. Early in Earth's history, sunlight was slightly dimmer. In the distant future, it will be somewhat stronger. This gradual brightening influences planetary climates over geological time, shaping atmospheres and surfaces. Several billion years from now, the sun will exhaust most of its core hydrogen. Fusion in the core will slow. Gravity will compress the inner region more strongly. Temperatures will rise until hydrogen begins fusing in a shell surrounding the helium core. The outer layers of the sun will expand outward. The sun will become a red giant. As a red giant, it will grow vastly larger than its present size. Its outer atmosphere will extend outward, likely engulfing Mercury and Venus. Earth's conditions will change dramatically. Oceans will evaporate. The atmosphere will transform. Over time, the expanded sun will shed its outer layers into space, creating a glowing shell of gas known as a planetary nebula. At the center, the remaining core will persist as a white dwarf, a dense, slowly cooling remnant, roughly the size of Earth, but containing about half the sun's original mass. No longer powered by fusion, it will radiate leftover heat gradually over billions of years. Long before that far-off transformation, the solar system will continue its quiet rhythms. Planetary orbits will shift slightly due to gravitational interactions. The moon will drift farther from Earth. The outer planets will circle in their long arcs. Beyond the immediate family of planets lies the broader galactic environment. The solar system orbits the center of the Milky Way at a speed of roughly 220 kilometers per second. One orbit takes about 230 million years. Since its formation, the solar system has completed only about 20 such galactic years. As it travels, it passes through different regions of interstellar space. Passing stars may gently disturb distant objects in the Oort cloud, sending some inward as long-period comets. The solar system remains part of a larger stellar community. Far beyond Neptune, icy bodies move slowly in darkness. Sunlight is faint. The sun appears as a bright star among many. Yet, gravity continues to bind these distant objects to their origin. Tiny dust particles drift between planets. Sunlight reflecting off this dust creates a faint zodiacal glow under dark skies. Even in apparent emptiness, material remains. Over immense timescales, gravitational interactions may alter planetary orbits slightly. These changes unfold gradually, guided by the same physical laws that have shaped the system from the beginning. Observations of distant stars reveal that many possess their own planetary systems. The solar system represents one arrangement among countless possibilities. Its particular configuration allowed conditions suitable for liquid water on Earth. Subtle influences, such as the presence of a large moon and the gravitational role of Jupiter, have shaped its history. From Earth's surface, the solar system reveals itself through cycles. The sun rises and sets. The moon changes face. Planets wander against the stars. These motions are predictable, steady, and enduring. Space remains silent. Explosions, storms, and impacts occur without sound. Light travels freely. The sun continues to shine. Eventually, after billions of years, the sun will become a white dwarf, and the solar system will grow dimmer. Planets will orbit a cooling remnant star. Far in the future, gravitational encounters may slowly disperse remaining bodies. For now, the solar system rests in a calm middle age. The sun shines steadily. Planets circle in established paths. Moons rise and set over distant landscapes. Comets trace long arcs between darkness and light. All of it unfolds in measured silence, suspended in the vast darkness of space, moving together through time without haste.